In this tutorial, I'll build on the hot water loops tutorial and discuss the key considerations when modelling chilled water loops. During the tutorial, I'll show you how to add a chilled water loop with Fan Coil Units by loading a HVAC template. I'll review the edit dialogs for the loop and the system components. And finally, I'll run a quick simulation and discuss the results. The system selected for this tutorial has been deliberately simplified to enable me to focus on the chilled water loop without unnecessary distractions, hence the omission of an air loop. I'll start by loading the Fan Coil Unit HVAC template here in the Model Data HVAC tab. Given that the data in this tab is also used for heating and cooling design calculations, it is good practice to get into the habit of ensuring the correct options are selected for your HVAC system from the outset. My Fan Coil units will provide heating and cooling, but I'll switch off mechanical ventilation as I won't have an air loop. Chilled water loops provide chilled water to cooling coils in components such as air handling units, zone air distribution units and chilled beams, and also to the pipes in chilled ceilings. I'll now go to the HVAC system and load the Fan Coil Unit 4-pipe air-cooled chiller template from the toolbar icon here. I'll add the system to all zones using the selected options here below the zone list to overwrite the existing HVAC system. This override template defaults option enables me to modify the main template default settings. I'll retain the defaults. The default chilled water supply subloop includes a single chiller, splitter and mixer, a circulating pump and a set point manager. The splitters and mixers here in the supply subloop provide the connections to enable you to add chillers. The demand subloop is automatically connected to the supply subloop and provides the splitter and mixer connections required to connect the loop to other system components such as air handling units and zone terminal units. I'll now review the edit dialogs for the system components, starting at the chilled water loop level. You'll already be familiar with many of the edit dialogs after viewing the hot water loop tutorial. So unless I think they're worth reiterating, I'll ignore inputs which don't require further explanation. The loop is set to variable flow here by default, which automatically sets the chiller flow mode to variable flow also. This load distribution scheme is only used when there's more than one chiller on the loop, and the basic details are described here in the info panel. This will be discussed further in a tutorial covering plant sequencing for loops with multiple plant objects. Much of the data on the plant loops dialogs are used for sizing to ensure that the loop can meet the loads created by the connected zones. The loop flow temperature used to size the loop is set to 6 degrees C, with a relatively small differential here of 4 degrees C, giving a return temperature of 10 degrees C. You'll need to make sure these reflect your system design temperatures, as they can have a significant impact on efficiency. For example, increasing the flow temperature by 1 degree C could reduce chiller energy consumption by around 3%, assuming the same differential is maintained. Similar savings may be achieved by increasing the loop temperature difference. I'll change this delta T to 6 degrees C, giving a return chilled water temperature of 12 degrees C for loop sizing purposes. The outside temperature operation option here allows you to restrict the external temperatures below and above which the plant or condenser loop will operate. This control can help prevent the plant cycling at very low loads. The temperature range should be set according to the type of plant loop. The external cut-in temperature is the outdoor temperature above which the plant is enabled, and the cut-out temperature is the temperature below which the plant is off. A reasonable deadband should be maintained between these limits. Going to the chiller edit dialog, the constant COP chiller type simplifies the simulation but doesn't use the performance curves, so will inevitably provide less accurate results under part load conditions. The default electric EIR option enables the simulation to model the effect of variable efficiency during part load operation by using these performance curves loaded with the chiller template. You should select the correct chiller model if it's included within the library. Otherwise, it's recommended that you use the air-cooled default chiller, which gives reasonably accurate results across a broader range of operation for an air-cooled system. Both the reference capacity and the reference chilled water flow rate are auto-sizable. If you manually input a value for one, you should also input the other value and not mix auto and manual sizing at component level. Consider initially leaving everything set to auto size when setting up the model. Once you've confirmed that the HVAC system runs correctly, you can then start to modify the sizing inputs and checking results systematically. The initial result set may also give you some useful data to compare your system design against. The reference COP, or coefficient of performance, is essentially the efficiency of the refrigeration process at rated output, excluding auxiliary energy consumption from components such as pumps and condenser fans. The relatively high COP value is consistent with an efficient centrifugal chiller, which you can see from the performance curve descriptions is what this template is based on. You should check that the data you're provided with is consistent with the description in the help file before entering this value, i.e. that it does not include auxiliary energy consumption. The chiller flow mode is defined at loop level. The sizing factor allows you to size a particular chiller in a multi-chiller loop to meet part of the design load while continuing to use the auto size feature. The sizing factor would adjust the cooling capacity and water flow rates for that chiller in the simulation. So two chillers of equal capacity in the same loop would each have a sizing factor of 0.5. The condenser fan power ratio is the ratio of the condenser fan power to the reference chiller cooling capacity in watts per watt. During the simulation, the condenser fan power for air-cooled or evaporatively cooled chillers is calculated as total chiller power consumption multiplied by this ratio. Performance curves are loaded by default with the chiller template. You can load your own chiller details and curves if required, but this should only be done with caution. See the help file for more information on performance curves. The part load settings can have a significant impact on efficiency, as many HVAC system chillers will operate at part load for significant periods of the year. If the minimum part load ratio for a chiller is set to 0, the chiller's condenser fans will continue to run, even under no load. Setting this to 0.1 means that the chiller and condenser fans will cycle off when the cooling load drops below 10% of the chiller capacity. The optimum part load ratio is only relevant when there are multiple chillers on the loop, and the optimal setting is used in the plant loop distribution scheme field. Compressor false loading is far less common in modern chillers, as it results in very inefficient part load operation. So if the minimum unloading ratio is set equal to the minimum part load ratio, the compressor will simply cycle off without false loading once it reaches the minimum part load ratio. I'll set it to 0.1 and click OK to accept the changes. The supply subloop includes a set point manager, which acts as the main controller during the simulation. The set point manager calculates the set point, in this case for the chilled water flow temperature node, which is used in the loop as a goal for control actions. The set point manager is set up by default to control the chilled water flow temperature to a constant 10 degrees C. To use the scheduled method, I need to set the loop flow temperature to 6 degrees C so that the operating temperature is consistent with the temperature used to size the chiller in the loop edit dialog. I simply copy and edit and change it to 6 degrees C . Remembering to load the schedule once it's been created. I also have the option to use the outdoor air reset to vary the chilled water flow temperature according to the outside air temperature. This can improve the efficiency for some designs by allowing higher chilled water flow temperatures to be used as the outdoor air temperature and the associated cooling load reduces. The pump control type is fixed at either constant or variable depending on the setting made at loop level, and the dialog is the same as that used in the hot water loop. As I've now added cooling to my system, I should go to one of the zones in the zone group and check that the cooling sizing defaults are suitable. The cooling sizing factor here is based on the ASHRAE standard. I'll leave it set at default. I haven't changed any of the fan coil units, so can check these in any zone knowing that they'll be the same in all zones. Energy Plus FCUs are basically small, self-contained, in-room, forced convection hydronic units. I either use water as the heat transfer medium. The 4-pipe FCUs in DesignBuilder provide both heating and cooling, but you can model a 2-pipe unit providing only heating or cooling by navigating to the appropriate coil and setting the availability schedule to off. There are 4 options available to enable you to define how the fan coil unit output is controlled by varying the air and water flow rates. Most of these are self-explanatory. Note that setting the cycling fan option allows you to set the low and medium fan speed ratios, with the high speed ratio defaulting to 1. I'll leave it set at constant fan variable flow. 2 fan control types are available for this option. Either the default on-off fan, which will cycle the fan on and off with load at constant volume when on, or the constant volume fan option, which will keep the fan running when scheduled on regardless of the load on the FCU. The outdoor air supply option enables you to model an outside air supply via a simple duct or directly connected outside air vent. As the FCU is directly connected to a fresh air supply, it's not possible to schedule the outdoor air option separately, so it will always have a fresh air supply when operating. This may be detrimental during periods of reduced occupancy, and when the system is trying to maintain the building above the setback temperature outside occupied periods, for example. The FCU is scheduled on by default, so it's available to operate on demand according to the Model Data HVAC tab Heating Operation Schedule unless restricted elsewhere. Restricting heating or cooling at specific times or dates could be done via the appropriate coil availability schedule. I'll provide an outdoor air supply in all zones. After confirming those changes and closing the edit dialog, you can see that the FCU now has an outdoor airflow in and out and a recirculation damper to enable the zone heating and cooling demands to be met without excessive airflow rates. The fan and heating coil objects are the same as those shown in earlier tutorials. The cooling coil type option here enables you to enter detailed parameters for the coil if required and available. The least complex coil options are set by default for the coil and analysis types. The schedule is set so that the coil is always available to operate when there is a cooling demand, but you could load a different schedule here if you wanted to restrict coil operation or even disable cooling. I've just run a simulation from the 7th to the 13th of April, which is an interseasonal week requiring both heating and cooling. The building level fuel breakdown results show that the heating system is operating mainly in the mornings, with limited heating and cooling after the building has reached its set point and is fully occupied. The chiller is operating in the afternoon on most days to provide cooling. Going to the ground floor east office, we can see that the system is meeting the heating and cooling set points of 22 and 24 degrees C respectively. The zone heat balance shows a significant amount of zone sensible cooling, most of which is provided by the introduction of relatively cold fresh air. The system load graph shows that there is a relatively small amount of cooling required by the chiller. Although the fan coil unit is scheduled on at a constant fresh airflow rate, the total fresh air graph appears to show variable airflow rates. Checking the scale on the y-axis, you can see that the variation is actually quite small and is a result of changes in the relative density of internal and external air as the temperatures change in time. Providing uncontrolled fresh air via FCUs may not be sensible in many climate zones. A much more flexible way to model outdoor air through fan coil units is to introduce a separate air loop which allows economizers, heat recovery and advanced controls to be included. In this tutorial, I've shown you how to add a basic chilled water loop serving fan coil units and then reviewed the dialogs. Now that we've covered the main loop types, we'll start to take a more in-depth look at the different types of system that can be modelled using those loops, and just as importantly, how we ensure those systems are correctly controlled.